Can you hear me in Zoom? Okay, let's get started. Hello, everyone. Welcome back to another lecture in digital design and computer architecture. Today, Professor Mutlu is traveling actually to IMW International Memory Workshop. So that's why I got this opportunity to teach this exciting lecture about caches. So first, quickly to jog your memory, here are some readings for yesterday lecture and today lecture. So I recommend you guys to check. So recall that the problem that we've been focusing through the previous lecture was that we wanted to design a desirable memory, let's say ideal memory, for example, having zero latency, access latency, having infinite capacity, and so on and so forth. But we realized that basically having ideal memory requirements, they oppose each other. For example, bigger is slow, faster is more expensive, and also higher bandwidth is more expensive. So the way that we try to deal with this issue, so we designed memory hierarchy. So we wanted both fast and large. Basically, we decided to have multiple levels of storage, progressively bigger and slower as the levels are farther from the processor. And ensure most of the data the processor needs is kept in the fast or faster levels, essentially. So that was the idea of memory hierarchy that we have discussed yesterday. And this is a picture, for example, that we can have many different levels of caches and main memory, and also in modern memory hierarchy, we should also consider main memory and also disk. And this can be also go to some remote memory accesses as well. So memory hierarchy in general can be actually quite, I would say, heterogeneous and has different levels of memory. And remember that the main reason that this idea was working was because of having a temporal locality and a spatial locality that we usually observe in our applications. So temporal locality basically refers to if you access an address, very likely in near future, you're going to access it again. So that's temporal locality that talks about your possibility of the accesses in the time. And we also look into spatial locality to say that basically, if you access an address, you will likely access also the adjacent addresses in the memory. So that's, for example, when you work with arrays, vectors, and also when you fetching instructions in an instruction string, you usually have a lot of spatial locality. So that's why actually this idea of caching and having memory hierarchy was quite successful and was helping a lot. And basically, we reached to this point that we wanted to design cache that we couldn't continue because of the time limit. So we will start with very simple cache, how we can design quite simplified cache design, and then we're going to discuss some of these important design decisions, and hopefully we will get to some more advanced topics in the memory hierarchy and cache design. So let me redefine the word of cache, because this is not only the processor cache that we are talking. Actually, cache has been used in many different domains in computer system. So essentially, cache can be considered as any structure that memoizes, use, or produce data. So basically, to avoid repeating the long latency operations required to reproduce or fetch the data from scratch, you might need to fetch, like you need to access the memory to bring data. And so you put that data into your cache such that you don't need to pay for that long latency memory access again. But you can also think of in other way around, like, for example, you need to do a lot of computation to generate some results, some value. And then you try to memorize those values in a computer structure, in a table. And then hopefully you can instead of reproducing those results, you can just fetch from that cache. So cache has been, as I said, used in different topics in computer system. One very good example is actually web cache, that you might be aware of that. Essentially, when you are accessing, when you are opening pages through your browser, the operating system has a software, has implementation that tries to cache some of the materials that you need to open these pages. And such that for future accesses, hopefully you can, start showing you the pages much faster. And then it loads from the basically structure that can be stored in the memory or also in the disk. And of course, some stuff also should come from the network, but basically that web caching can help you to, will improve your user satisfaction. So cache, as I also most commonly in the processor design context, and automatically manage memory structure. But this can be also programmer managed. It can be actually software managed. So we will discuss a lot in this lecture about how we can have a hardware cache, which is automatically managed by the processor and the hardware. But this can be actually also software cache. That it's a job for the programmer, or also can be partially compiler, to manage that data structure. This is called actually scratchpad memory in different contexts. In NVIDIA GPUs that we have covered in previous lectures, they call it, for example, shared memory. And I will show some slides later. But essentially, not all caches are hardware controlled. It can be actually also software controlled. So if you got this question, for example, in the exam, that is handling cache is dependent on, is a ISA problem or microarchitecture problem, then your answer should be, it depends. It depends how you react or interact with your cache design. So later on, I think next week, we're gonna also learn about prefetching. And there are some instructions that you use these instructions to prefetch data earlier the moment that you want to the cache. And those can provide better performance. So basically, this is something that you should also get, start thinking about it as of now, that this might be also not always hardware controlled. So the example in our processor architecture is that we want to memorize in fast SRAM the most frequently or recently accessed DRAM memory locations to avoid repeatedly paying for the DRAM access latency. And that's essentially what we are talking about for the hardware cache. So this is a conceptual picture of a cache that in your cache, you should have some basically cache blocks that you basically chunk your data into several blocks. And usually when we are talking about hardware implementation of caches, we want to have same size for all these blocks in order to simplify the implementation. Even though there were also some people and researchers that they try also to look into variable block size. But overall, in order to simplify the design, people wanted to have basically exact the same cache block size in a hardware. But when you're implementing cache in the software, you have much more flexibility. So you can actually have much different variable size block sizes. But that's also another topic that unfortunately we don't have time to cover. Each cache block, essentially you have data that, for example, it can be 64 byte, as we also mentioned in the previous lecture. And there should be also some metadata that we call it tag, in order to such that you can understand that this data or this data is stored in the cache is corresponded to which address. So that tag is helping you. And that's not only the only information that we store in tag. We also need to store some other informations in the tag. For example, whether or not we have accessed this the cache block, or for example, is it valid or not? For example, so all these actually metadata needs to be defined in this tag array. So logical organization of a cache. Basically, our key question here is that how to map chunks of the main memory, chunks of the main memory address space to blocks in the cache, or essentially which location in cache can a given main memory chunk be placed. So here is an example that, for example, we consider each chunk is 64 bytes, and then you can actually chop your memory address space to equal size 64 bytes. So depending on how large your memory has, that defines the number of cache blocks you have. But then your cache is a limited space memory. So of course, you cannot map everything. Like you cannot keep all these cache blocks at the same time in your cache because of the capacity limitation. So you should have a solution to understand that basically one of the very first fundamental questions to answer is how we map a chunk of the physical address space to our cache. And that actually the answer to this question brings us to three major ways of implementing cache, which I will first start with fully associative here. So in fully associative, basically you can map each chunk, no matter about the address of it, to essentially every cache block or any cache block that you have in your cache. So, for example, if your cache is completely empty and you have a chunk of data or cache block, you can basically map it to cache block 0. And then another future access is another cache block, like cache block, let's say 100, and then you map it to the cache block 1, for example, and so on and so forth. Basically, there is no limitation except the cache capacity here. And you can actually map cache blocks to every location in your fully associative cache. On the other hand, you can actually, on the other extreme, you can have a direct map cache, which essentially for each cache block, depending on its address, you can have only one location in your cache. So basically, depending on this chunk address, or let's say cache block address, you use a part of that address in order to map your cache block to a specific cache block in your cache design. We're gonna learn to see that actually that function is so simple. It can be complicated, but usually people make it so simple, for again, for simplicity reasons. But that actually makes it so strict, essentially. So if basically, if you have several chunks, several cache blocks that they are mapping to the same cache block, that can cause to some issues that we're going to learn later on, that we call it conflict misses. You map, for example, cache block 0, basically to this first cache block. And then later on, you have another cache block, which is cache block 4. And then essentially, you need to map the same that block to this cache block 0 again, because your function is telling you that the location for that cache block should be cache block 0. And then you need to basically evict the previous cache block that you have stored here in order to make room for this new cache block. And later on, if you have access to cache block 0, like exactly cache block 0 or memory address 0, you're going to see that now you have this conflict miss, because you are missing because you basically evicted and that block because of conflicts happen in your future access, in your previous accesses. So something in the between is actually set-associative. So you can basically have several sets in your cache design. And then so basically you use a part of your address, or we will call it actually index later on, in order to index the address to a set. And within that set, you have this freedom to put your cache block on each of these locations. So here we are, for example, showing two-way set associative, but it can be four-way, it can be n-way, essentially. And the extreme case of set associative is actually also fully associative, that you essentially have only one set. So in fully associative, you have only one set. And in direct map, actually, basically, so basically you can call fully associative and direct map, both of them using the definition of set associative. So in fully associative, you have only one set, and every block is actually stored in that set. But in direct map, actually is like one-way set associative. So basically, you have all these sets, and in each set, in direct map, you have only one cache block. So you can call it one-way set associative. Any question? We're gonna see with more detail and examples, but I wanted to just prepare your mind. But question? Okay. So let's start with some cache basics. First, the definition of block line that I've been also using it. That's a unit of storage in the cache. Actually, cache block and cache line has been used interchangeably. Unfortunately, there is no, there is no exactly the same terminology. So even in one paper, in one book, you might see both cache block and cache line. But essentially, memory is logically divided into blocks that map to potential locations in the cache. On a reference, meaning that when processor, for example, requests loading a cache, loading a memory address, can be byte, for example, you can have heat if in cache, use cache data instead of accessing memory. So if you can't find your data that you're looking for in the cache, you have a heat. And on the other hand, you have miss that you cannot find it in the cache, and then you need to bring back the data into the cache from lower levels. And that may have to evict some other block, because the capacity of your cache is not infinite, and you might be basically you might have to evict some other blocks in order to make rooms for your current blocks. So there are actually several important cache design decisions that we're actually going to look into them in today's lecture. One of them is placement. So where and how to place and find a block in the cache. Another important topic is replacement. So what data to remove to make room in the cache? Basically, replacement is a topic related to what to evict, essentially, when you want to make the room. But placement is saying that when you want to put the data in your cache, how you are putting that, how you're inserting that in your cache. Another important topic is granularity of management. Are you going to basically work on with large or small blocks? Or we can also have sub-blocks that we're going to actually see today. How you manage writes. So your write policy is also another important topic that we need to look into. What do we do about writes? And also instructions and data. Do we treat them separately or in a unified memory? We're going to hopefully learn about all of them today. These are most of the some important cache design decisions, but there are also many other important design decisions that people have been looking into when they want to design memory systems. And actually, these topics have interested a lot of people during the several years, I would say several decades, actually, that to improve the cache performance in our system. Okay. So let's start with some cache abstraction and metrics. I think we already also seen this definition of hit rate in the past. So when you have an address from your processor, essentially, so you need to send your address to your tag store and also data store. Remember that we say that in each cache block, we should have a data and also some metadata that we call it tag. So usually, actually, people use two different separated array for it. So we have a tag array, which we call it here tag store, or we also have data array, which we call it data store here. So when you send your address to both tag store and data store, and the job for tag store is to say that is the address in the cache, essentially. So have I cached this address before or not? So that's the definition, and I actually use some bookkeeping techniques or so. But in the end, the result for tag store should be hit or miss. And depending on that, basically the data that you fetch from your data store might be useful or not. So there are also some ways that we're going to learn later that we access our data store only when we have a hit. We're going to learn about it. But normally you can think of at this abstraction layer that you access both. And if it is a hit, basically you have a valid data out of your data store. But if it is a miss, then you should not use the data that you are reading from your data store. So cache hit rate is one of the performance metrics that you can think of, which is number of hits divided by number of hits plus number of misses, or number of hits divided by number of accesses. And using that, we have another important metric, which is average memory access time, which is essentially hit rate times hit latency plus miss rate times miss latency. And from previous lecture, actually, you should know that miss latency is because we have a hierarchy, and miss latency is hierarchical. So depending on the hit rate and miss rate on other levels of hierarchy, you should calculate this miss latency, and that would affect the total average memory access time for you. But there is an important aside here that I want to mention it. I'm not answering it at this moment. Just to prepare you can start, think about it. So is reducing average memory access latency always beneficial for performance? Meaning that if I basically put that as my main goal in order to reduce AMAT, average memory access time, would that affect the end-to-end, like the execution time of my application or not? Because that's the bottom line performance metric that we can basically are caring about, right? So we want to see in the end, I should care, but locally I care, but globally, I mostly care that how fast my processor is running my application, right? So when you reduce average memory access time, would that always beneficial for performance? Or maybe the other way around is that, should I always shoot for better average memory access time or not? So that's I think you can guess the answer to it. Probably the answer is no. But why is that? That needs some discussion that we're going to hopefully get to that through the end of this lecture. Question? Okay. So we will start with the basic hardware cache design, and then we will examine the multitude of ideas to make it better. So remember this way that we have this, we chunk the memory address space to 64 bytes, and we are starting with a toy cache example that we can store 4 blocks here. So each block address maps to a potential location in the cache, and that determined by the index bits in the address. So we use the index into the tag and data stores that we already showed. So this can be your address space, like the address bits. We are assuming here 8-bit addresses. So that means basically your memory, assuming that basically your memory is byte addressable. Since your address is 8-bit, you have 256 bytes. So that's the size of your memory. And this is one way of basically showing, like dividing the different bits for your cache. So here we are considering that we have 3 bits to show which byte I'm referring to in the cache block, which means that I'm using 3 bits to basically point to a specific byte in that cache block, meaning that we have 8 bytes. So we talk about 64 byte in conventional system, but here for a toy example, we are considering that our cache block is 8 bytes. So that's why we are using 3 bits here in order to specify which byte we are referring to. And then we have this index bit, which is 3 bits of this address that we will use, for example, to index our cache array, both tag array and also data array. And then we also have 2 bits as a tag that you're going to see that we will compare the tag of our address to the tag of the address that has been stored there. If that's a match, then we have a hit, for example, in our cache. So when you have a cache access, basically, to summarize, you index into the tag and data store with index bits in the address. Then we check valid bit in the tag store because we want to make sure that that entry is valid. When your cache, so valid bit is there just to specify that this block is empty or not. So in the beginning, your cache is completely empty. So all valid bits are reset essentially. But as you insert cache blocks to your caches, basically you change valid bits to 1 to show that they are valid cache blocks. Sometimes also you use valid bit for some other reason that we want to say that this cache block that I had before is not valid anymore. And that's, we may actually get to that also later today, which is the topic of coherence, cache coherence. Okay, the third step is to compare tag bits in address with the store tag in the tag store, which is we use this tag to check that. And then if the store tag is valid and matches the tag of the block, then the block is in the cache, and we call it cache hit. Okay, so let's work with our toy example. We will start with the direct mapped. A given main memory block can be placed in only 1 possible location in the cache. So that's the definition of basically direct map cache. So we are still assuming the same memory, which is byte addressable main memory, and we have 256 bytes in the memory. Our block is 8 bytes, meaning that in total we have 32 blocks in the memory. So this is this shows actually your main memory, all the blocks that you have from block 0 to block 31 essentially. So your memory has 256 bytes, but since each block is 8 bytes, in the end you should have 32 blocks. And you can see that the address we are showing for each block is only 5 bits. So we're kind of basically ignoring, because we don't need to show like the first 3 bits least significant bit of the address, because those 3 bits are gonna be used to show which byte we are referring to in that specific block, right? So that's why you are saying that you're seeing only 5 bits. However, your memory address space, actually memory address is 8 bits here, but your block address is only 5 bits. Makes sense, right? Okay. So we assume that our cache has 64 bytes and 8 blocks. So in a direct map, a block can go to only 1 location. So we have a tag store and data store. In our data store, we have 8 blocks, as we assume here. And this is a tag store. Here are the valid bits. And also we need to keep tag bits for each of these blocks. So, and this is how you use your address in order to access your cache. This is very similar actually to our example in the previous slide. So your address is 8 bits. You know that your block is basically 8 bytes. So essentially you need to use the first 3 bits, least significant bit, as in order to point to a specific byte in that block. So that's the usage for the first 3 bits. Then we need to index this both tag store and data store, and we have 8 elements. So essentially, we need 3 bits in order to point to that. Log 8 over 2 is 3. And the rest should be tag, essentially. So since we had 8 bits, so 8 minus 6 is going to be 2. So we are using 2 bits for tag array here as well, for each address. So when you send an address, essentially, you index your tag store and your data store. So in the tag store, you check if it is valid. And if it is valid, then you basically fetch the tag stored in that specific location that you actually pointed out using that index. You compare that tag with the tag stored with the tag you have in your address. And if they both equal, then you have a hit. And if it is a hit, then you can get your data from your data store. You also have a multiplexer here because from this data store, you are reading the whole cache block. But then you might want to basically read only 1 byte out of it, because depending on the instruction of the processor, might be load bytes, might be, I don't know, load half word, load word, or load double word, for example. So depending on this that instruction, you might want to load, read only 1 byte, 2 bytes, I don't know, 4 bytes, 8 bytes, and so on and so forth. So, but there should be a multiplexer here in order to specify the byte that you're looking for, essentially. Any question here? Looks simple, right? I hope so. Okay. So essentially, in direct map, blocks with the same index content for the same cache location. In this example, we are showing them, for example, with this green highlight, you can see that block 0, block 8, block 16, and block 24. All of them are will map to this basically cache block 0 here, right? And that can cause this problem of basically conflict that I said. For example, you processor access a word which is stored in this block 0. So you move that block 0 to your cache. And then hopefully in the future, you're going to have also some other accesses to that block 0 that you're going to enjoy your heat. But then later on, you have another access from processor that address belongs to block 8. So essentially, you need to move block 8 to your cache. But since there is only 1 location for that block, you need to evict the block 0 from your cache, essentially, both tag store and data store. And then you move your block 8 to that. So later on, if you got another request that belongs to block 0, now is a miss, right? Because block 0 does not exist in your cache anymore. So we call this situation as a conflict miss, essentially. And direct map is very bad because it can cause conflict miss, even though we might have empty spaces in our cache. So conflict miss is actually different from capacity miss that we're going to see later on. Sometimes you might have miss because, okay, your cache is full and you have to evict something. But with conflict miss, you might still have some empty spaces in your cache that you should be able to use them, hopefully. But since with this your mapping, which is direct map, which is quite strict, you cannot freely map your cache block to any location in your cache, and that can cause conflict misses for you. Okay, so to summarize, essentially direct map cache, 2 blocks in memory that map to the same index in the cache cannot be present in the cache at the same time. So 1 index, 1 entry, and can lead to 0% hit rate if more than 1 block access in an interleave manner map to the same index. For example, with this example, assume addresses A and B have the same index bits, but different tag bits. For example, in our example, block 0 and block 8. If we access AB, 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 so they all conflict in the cache index. And then basically all accesses are conflict misses and your hit rate is 0, essentially. And that's why direct map can be actually sometimes very bad, depending on your access pattern. But from the upside, direct map caches are very simple and easy to implement. And that's why they are also useful in some context. Okay, so how we can fix the problem? Essentially, we will make more freedom. You know, we say that I don't have to map my block only to one place. Hopefully, I should be able to at least map it to 2 places, for example. So that's a problem. That's the idea that we're going to use, which we call it set-associativity. So basically, the idea is that we enable blocks with the same index to map to more than one cache location. So the example is that instead of having 1 column of 8, we can have 2 columns of 4 blocks, which we call it two-way set-associative block that you're going to see. So this is our now tag store. So we make 2 columns. Each of them has 4 entries. And also you need to do the same for data store. Now, essentially, you need to compare more. So when you have access, you need to check the valid bits of 2 blocks, 2 basically tag locations. And also you need to compare your tag with the tag stored in both places. And if it is a hit, then you can get your data from your data store. And then again, here also there should be a multiplexer to say that from which basically column or block you need to get your data. And then you need to add another multiplexer in order to specify which byte you want to get. So this actually, you can see that this complicates the design, and you're adding more hardwares. But this can help heavily help us in order to reduce conflict misses. So the key idea here actually is very also similar to associative memory within the set. Actually, I think you should remember from our out-of-order processor design, we were talking about content addressable memory in order for implementing a reorder buffer, for example. So content addressable memory is essentially the memory that you put the content and also the address at the same time. And in order to find your data, you need to actually you need to search through that set and compare the address, which is stored in that entry with the address that you are looking for. So that's called it CAM, or content addressable memory. And essentially in set associativity or set associative cache, you need to do that search within that set. So within each set, you have this content addressable memory that you need to search and find your tag if it is stored there. Any question? Okay, good. Okay, we already discussed all of them. So we might need higher associativity. For example, in our example, we say that we might have AB, 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 AB. So that with direct map, we have 0% hit rate. With two-way set associativity, we can actually have very good hit rate. If we ignore the first 2 misses, so basically you access A the first time is a miss, and then you access address B for the first time, that's also a miss. But then later on, if you just repeat these accesses, AB, 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 all of them are going to be hit in a two-way set associativity cache. But the problem can be worse. It can be ABCD, 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 right? So with that, in that example, for example, two-way set associativity cannot work. Again, you want to have 0% hit rate. Now you know the trick. You do this 4-way set associativity. So you can basically divide your tag store into 4 columns and also data store into 4 columns. And then you need to compare more. So you need to add, for example, 4 comparison here. So your tag, basically the hit checking logic is getting more complicated and more costly, essentially. And this is how the address will look like here, right? So we still need to use 3 bits in order to show which byte in that cache block we want to access. But then now we have only 2 sets, right? So we have only 2 sets here. And so then in order to index 2 sets, I only need to use 1 bit, essentially. So that's why my index bit here is 1 bit. And the rest is going to be tag. So you need to store more tags also when you have higher associativity, and that can also increase your tag array capacity, essentially. But then, yeah, the likelihood of conflict misses are even lower, which is good. And in the extreme case, you can have this fully associative cache. A block can be placed in any cache location. In our toy example, basically we can have one set with all 8 blocks are basically stored, can be stored freely in that set. So essentially, whenever you want to search or find your cache block in your cache, you need to compare 8 tags. You can compare it in parallel, like what we showed here, if you want to have very good access latency. But you can also think of doing this comparison in a serial manner. That can reduce the number of comparators you need, but that comes at the price of longer access latency, essentially. So that's a trade-off that people also have looked into it. And if you have a hit, then you can get yours. So now you need a larger multiplexer in order to decide which cache block you're reading, and then another mux for deciding on the byte. So yeah, so I think it makes sense. But any question? Good. So in the address, essentially we have 3 bits for the byte, and then the rest is going to be 5 bits, meaning that the index bit here is 0, because we don't need index at all when you have fully associativity cache, because you have only one set. So you don't need to, you don't have anything to index to your cache, essentially. So we already talked a little bit about the trade-off, but here I want to show a bit more. So the degree of associativity, how many blocks can map to the same index or set, essentially the number of ways. So higher associativity would probably cause a higher hit rate. This is actually this is likely. Of course, it depends on your access pattern. If your access pattern does not have much of temporal locality and spatial locality, you might not, benefit much from set associativity as well. But on average, across many workloads that people have used, they show that basically by using higher associativity would cause higher hit rate. But at the same time, it comes at the price of slower cache access time. So hit latency and data access latency, they are longer. And you need to add more hardware. So more expensive hardware, more comparators, more area, more power, and so on and so forth. And the problem is that we have people show that the return diminishes from higher associativity, meaning that when you go from direct map to 2-way set associative, you're going to see a lot of good improvement. And then from 2-way to 4-way, you're going to still see, for example, very good improvement. From 4-way to 8-way, less improvement. From 8-way to 16-way, even less. And then at some point, the benefit you're getting from better hit rate does not convince you, because you are increasing the access latency of your caches, and the benefit that you're getting from better hit rate does not justify your decision anymore. So this is like the graph pictorially that usually look like this, that when you increase your associativity, hit rate increases, but of course we have these diminishing returns from higher associativity, and basically we saturate at some point, which makes sense, I guess, right? Because the reason that set associativity is helping us is because to reduce conflict misses, right? But conflict misses are not the only reason that you have miss in your systems. At some point, you cannot, so by going from direct map to, for example, 4-way set associative, you reduce conflict misses a lot. And that's very good. But from 4-way, for example, to 8-way, the amount that you're reducing is not that much, and then that doesn't justify the complexity of the design anymore. Question? Okay. So let me go into some issues in designing set associative caches. So we should think of each block in a set having a priority. So indicating how important it is to keep the block in the cache. And the key issue here is that how do you determine or adjust block priorities? So now that we have several blocks in one set, whenever you want to evict, for example, one of them, because your set might be full, right? So you have, for example, in a 2-way set associative, you have 2 blocks in a set, and both of them you have used it for different blocks, and then you have another block that you want to move it to the cache, and then you don't have a space. So essentially, you need to evict one of the stored blocks. So which one you're going to select? So that's the problem of that we need to find a way to basically come up with a priority when we have these set-associative caches. So essentially, there are three key decisions in a set that we're going to look into: insertion, promotion, and eviction, which eviction is also known as a replacement. So insertion, basically what happens to prioritize on a cache field. So when you basically insert the cache block to your caches, how the priorities is going to change, essentially. So where to insert the incoming block, or whether or not to insert the block. Actually, sometimes you decide to not insert the block, and we're going to see also later on. So that's a decision that you need to make. Another important decision is promotion. What happens to prioritizes on a cache hit? So once you access a cache block, and that's a hit, then what would happen? How does that change the priority, essentially? So whether or how to change block priority in that set after some accesses to your caches. And the third important key decision is eviction and replacement. So what happens to priorities on a cache miss, essentially? So which block to evict and how to adjust priorities, essentially. So that's these three key decisions going to be the main thing that we're going to focus on for a few minutes for now. Okay, so eviction and replacement policy. So the question that we want to answer here is that which block in the set to replace on a cache miss, and basically first in any invalid block first. So if you have a space in your set, like meaning that there are some blocks in the set that they are invalid, meaning that they are still empty, so you just use them, right? So then your answer is simple. But of course, if all are valid, then you need to have a policy, which we need to consult with the replacement policy. There should be a policy, which we call it replacement policy, that essentially tells you that, sorry, that tells you which block you need to evict in order to make room for your, basically, for the block that you want to insert. So your replacement policy can be random. And people actually have shown that random replacement policy is also not a bad idea on average across many workloads. Of course, there might be some access patterns that random replacement policy would fail. But essentially in random, you say that I just roll a dice, and based on that, I will just evict one cache block, right? It can be FIFO, which is first in, first out. So basically the block that you insert to your cache at the earlier time, you consider it as a candidate to evict based on this FIFO policy, which might not be the good idea, because that block, you might insert a block to your cache block very early in the execution, but you kept using that block. So meaning that you kept accessing that cache block and you have cache hit. So by FIFO, you don't consider the fact that you're using that block. The only thing you care in FIFO is that when you basically insert that block in your cache. Let me finish this slide and then we can take a break. Another way is using least recently used, LRU, which essentially we're going to see how we can implement least recently used, and I will also ask you guys about it. But in LRU policy, basically you want to evict the block that you haven't used it. Basically, is it least recently used? So you haven't used it recently. So how we can implement that is actually a problem that we're going to also look into it. Another one could be, for example, not most recently used. So you have a track, you know that which block is the most recently used. So you make sure that you don't evict that block, but other than that, you don't care. So you may select any of the blocks that you might have that they are not most recently used. Or it can be least frequently used. Also, for example, it can be least costly to refetch. That why would memory accesses have different costs? So sometimes when you're evicting a cache block, you should think of, okay, how costly would be to refetch this block for me? Am I going to refetch this block again from the other cache hierarchy, for example, from L2? or I'm gonna fetch it from the main memory. So main memory has longer access latency, so your the cost in order that you're paying for refetching that is gonna be higher. So sometimes you should also consider that in order to have a better performance. You can also think of hybrid replacement policy. Remember that we use the hybrid branch predictions. You can also think of combining different of these different replacement policies in order to make a better technique. And you can also think of optimal replacement policy, which is very hard to do because it's very hard to, like, what does exactly optimal mean? In what metric, essentially? So optimal can be in terms of miss rate, for example, or in terms of the access latency, in terms of the execution time of your processor, or in terms of energy, for example. So definition of optimal is not clear, and at the same time, it's very hard to come up with the that replacement policy which is ideal, because essentially you don't, in order to have a good replacement policy, you should have information about your future accesses, and that information usually does not exist. Okay, so I think this is a very good point to stop, that we will discuss about implementing RRU in more detail. So let's get back when the ring bells, and then we will continue. Okay, so let's continue. Before I move forward, I want to remind you about our next Thursday lecture that has been shifted by 1 hour. I think you also got the email from the department. So basically make sure that you're attending at 1 p.m. That. Okay. So we discussed about LRU, which is least recently used, and now we want to see how we can implement it. So the idea for LRU is that we want to evict the least recently accessed block, which is essentially based on the fact that we are benefiting from temporal locality, and we want to evict the block which can hurt temporal locality less, essentially. So that's the key insight behind why LRU would be or is a good or can be a good solution for replacement policy. So the problem is that we need to keep track of access order of blocks. So the question we have here is that for two-way set-associative cache, what do you minimally need to implement LRU perfectly? Any thoughts? So how many bits I need to implement LRU perfectly, minimally, for two-way set-associative? Just guess, it's not that hard. Yes? 2, but why? But there are only 2 blocks. 1 is enough. So 1 is a minimal number here. So the minimal number of bits you need here is 1 in order to implement LRU. But how about 4-way set-associative? I'm asking the same question. No, it's not 2. Yes? No. But what's your logic to get 4? No. No, essentially you need to count the different, the number of possibilities. It's actually kind of a probability question, like how many different possible order you can have in a four-way associative cache. Maybe you can answer this. So how many orders I can have when I have 4 blocks? If you remember something from mathematics. So is yes? 24. Exactly. 4 factorial. Yes, perfect. Yeah, in the first location you can have 4 possible cases. The next one only 3. The next one 2, and then the third, the first one you have only 1. So it's like 4 times 3 times 2, 1. It's going to be 24, which means you need 5 bits in order to encode these 24 cases. But then you also need to have a logic, like decoding logic that get that 5 bits as an input, and output basically is telling you that basically which order are you in, like what block is actually the least recently used for you. But there is also another way in order that you store a bit more, but then that can simplify your logic. For example, if you store 8 bits, essentially you use 2 bits per block, so then you have 8 bits in total, and that's an easy way of encoding. So you're storing more bits now, so you're paying more capacity cost, but that provides you more simplified, basically decoding logic in order to understand what is the LRU. But essentially, in the end, you can repeat the calculation we have done for n-way set associative. So it's going to be n factorial, the minimal number. But as I said, sometimes people don't use that minimal number because that can also complicates your the decoding logic a lot. So people use like log n, no, not log n. Yeah, number of blocks times log n, exactly. Number of blocks log n, that can actually simplify the logic that you have for that. But as a conclusion of that, unfortunately, I don't have enough time, but as a conclusion, you can see that implementing LRU is actually costly in terms of storage space and also in terms of logic that you need to add. Specifically when you have a lot of ways. For example, when you have 8-way set associative cache and you want to implement LRU, is not easy. So people in industry and also research work a lot to approximate LRU. So most modern processors do not implement true LRU, also called perfect LRU, in highly associative caches. So there are actually two reasons for it. The first one is that true LRU is complex, as we already discussed. And the second one is actually LRU is an approximation to predict locality anyway. So no one said that actually LRU is the perfect way for doing this cache replacement policy. So maybe it doesn't make sense that we spend a lot of resource and time in order to design something which in the end is not going to be also perfect anyway. So that's why people try to use some approximation for LRU. Like, for example, one way is using not MRU. So we only we need to keep the most recently used. So that's easy. So you just want to know which block has been used mostly. And then you make sure that you don't evict that one, and the rest you can, for example, select them randomly. You can also have hierarchical LRU. I'm not going into detail of that, but just to give you the idea, you can, for example, you can make a hierarchy. In your set, you can chunk it to different smaller sets. In each of these smaller sets, you can have LRU. That can be also true LRU because you might have less number of ways in that smaller sets. But then globally, so locally you can have true LRU, but globally you don't need to have basically true LRU. So you can have some other way of using it. So for example, you can track the MRU group and the MRU way in each group. For example, this is one way of implementing hierarchical LRU. And another example is using victim next victim replacement policy. Essentially, here you make sure that you don't, for example, evict the most recently used, and also another block, one more. And that another block, there is a policy that you might have in order to select it. But I'm not going into detail of all these implementation, but essentially, just to give you this idea that people have tried to approximate LRU in order to simplify the design for the caches. Another question can be LRU versus random. So which one is better? For our example, like 4-way cache, and we have cyclic references to A, B, C, D, E. The thing is that we have 0% hit rate with LRU policy because, so you have A, B, C, D, and in your 4-way cache, all of them are stored in your cache, and then you get to the address E, right? So when you want to insert E, the least recently used is actually address A, right? So you basically, you evict A and you insert E. So the next A, because it's a cyclic references, the next A that you're going to access is going to be miss again. And then then you need to bring A, and then your least recently used is B. So your B is going to be miss also. So in the end, you're going to have 0% hit rate with LRU policy. So, and that's a problem that we call it actually set thrashing. So when the program working set in a set is larger than set associativity. Here, for example, we have 5 blocks that we are accessing them in a temporally way, consecutively. And that can basically, these blocks can cause thrashing in the set. which in the end can cause LRU not to work perfectly here. So in such cases, people have shown that the random replacement policy is better when trashing occurs. And in practice, actually, people show that the performance of replacement policy depends on workload. I mean, different workloads, we can have different replacement policy. And average hit rate of LRU and random are similar. So when you average the miss rate or the performance of them across many, many workloads, you can see that they are working overall the same on average. But when you're checking every workload separately, you can see that for this specific workload, LRU might be better. For that one, random might be better. Or even if you actually want to look a bit deeper, you're going to see that inside that workload, when I treat some sets in a random way, I can get better performance. And other sets should be LRU. And people actually also have tried that. Like they try to use LRU and random together in a hybrid manner. And then you can actually, the granularity can be even set-based. Like even for each set or some set sample of some sets, you can decide basically which LRU, which policy you want to apply, essentially. So you can, as I said, use hybrid, and then you have to choose between the two. You can have this set sampling, and then you basically, for some of the sets, you can have LRU, some other sets can have random, and so on and so forth. People also look into using some machine learning algorithms as well in order to implement replacement policy. Probably not for L1, because for L1, you need to be very, very fast, and you probably cannot afford the latency for complicated logic for replacement policy. But maybe for other levels, maybe L2, L3, you can actually have more complicated replacement policy, and you can use machine learning for doing that. So the idea of set sampling, you can, for learning more, you can actually check this paper. We're going to get to this paper hopefully through the end of this lecture, but for another reason, but you can also check this one if you are, for this reason, interested. Okay, so about the optimal replacement policy, people have also looked into it a lot. As I said, optimal replacement policy is not easy to do because, first of all, we don't know what is optimal. So there are many, many different metrics. And in Belidy's optimal replacement policy, that we call it Belidy's OPT, so we replace the block that is going to be referenced furthest in the future by the program. So essentially, you need to have the knowledge of the future accesses in your program. And that has been actually presented in IBM System Journal in 1966 basically for virtual memory. But how do we implement this? Actually, is it implementable? So probably no, because you need to have information from future. And if you think about it, that can actually cause the causality of the system, right? Your system might not be causal anymore because you need the information from future to implement your current decision. But you can predict, essentially. And all these replacement policies that we are thinking of, they are trying to predict the future, right? But you can also simulate it. People have looked into it, how to simulate. You can actually have a trace of your future accesses and then use this information in order to implement Belidy's replacement policy for your cache. And this can be used in order to show the gap, for example. So you want to, if you consider Belidy's replacement policy is the best, is the optimal one, by the definition of optimal, which in Belidy is actually the lower miss rate. So whenever you want to have lower miss rate, Belidy's OPT is the optimal one. So people have tried to implement that or simulate that in order to show the gap or the room that you can improve your cache by using better replacement policies. So for example, you know that by implementing LRU in this cache, my average miss rate, for example, is 10%. But then you also implement Belidy's and simulate it, and you see that your miss rate is 4%. And you can see that, okay, now I have 6% here, difference between LRU and Belidy, and that shows a room, for you to work on and improve, essentially. So it's always good to think about some oracle policies, which Belidy is also kind of oracle policy, that people think about implement to show what would be room in order to improvements. Okay, So validity is the basically optimal for minimizing miss rate. The answer is yes. But is this optimal for minimizing execution time? The answer to that is no, because as we're gonna also see later, that cache miss latency and cost, that varies a lot from block to block. So you don't pay similarly for different misses. Partly because of when you miss from L1, basically you might hit in L2 for some block. For some other block, you might also miss in L2, and you might miss also in L3, and you might need to get data from DRAM. So that cause cache miss latency and cost varies from block to block. There are also other reasons like memory level parallelism that can cause miss overlapping that we will hopefully see later today. But these things we'll discuss in this paper. If you're interested, you can also check. Okay. So we will hopefully get back to this paper later today. So now let's get back to more implementation details. So what's in a tag store entry? So we showed that we have this valid bit and tag, and there should be also some bits in order to implement our replacement policy. We might also have another bit, for example, dirty, which we call a dirty bit, and that can be used to control writes, that we're gonna see about write back and write through caches. Meaning that if you have a dirty bit, you can specify that this cache block I have already written to it, meaning that I changed the content of that cache block. So you can have a bit for that to show. Or you might not have that bit, and then you should have a different scenario, different techniques in order to handle writes that we're going to see now, actually. So this is important for handling writes. So when do we write the modified data in a cache to the next level, essentially? So you have a cache block in L1, and the processor sends a store request, for example, and that the store actually hits in your cache, L1 cache, essentially. So you change the data, that block in the L1 cache. So now the question is that when do we write this modified data to other levels, to the next level, to L2, L3, and DRAM, for example? So essentially, you can have two approaches here, which is write through one of them. At the time the write happens. So when the write happens, you update your cache, L1 cache, for example. You also update the other levels, essentially. You also update L2, L3, and memory, if they also have your cache block. You can also have another version, which is write back, which is when the block is evicted. So basically, you delay the updating the other levels until you have to evict this block from your cache. So for that, you need to keep this dirty bit, essentially, to say that, because when you want to evict this data, you need to check if this data or cache block is modified or not. If the dirty bit is 0, meaning that this cache block is not modified, you just evict it. You don't care. But if it's dirty, you should actually update also the memory as well, the other levels. So basically, you update the next level, and then after that, you can evict it. So that's the write back mechanism here. So let's see about like some pros and cons about these two techniques. So in write back cache, we can combine multiple writes to the same block before eviction, which is really good, right? So you are not sending every write to the lower level, and that can potentially save a lot of bandwidth between cache levels, and that can also save energy. So you filter, for example, a lot of writes in your L1 cache, and you don't send many of these to L2, and then you don't send many of them to L3, and so on and so forth. But you need a bit in the tag store that indicates the block is dirty or modified for write back cache. Write through cache is a simpler design, of course, and all levels are up to date and consistent, which is in the end, I think, through probably the next lectures, you're gonna see that this is simpler for cache coherence, because there is no need to check close to the processor cache's tag stores for presence. I'm not going to detail it right now, because that's a topic that we're gonna see later, hopefully. And then write through cache is bad for bandwidth, because it's gonna consume more bandwidth. So it's more bandwidth intensive. There is no combining of writes. So every write, you basically also update other levels. So you need to send and consume a lot of bandwidth, At the same time, you also consume a lot of energy for doing that. Question? So which one do you prefer, write back or write through? It depends. It depends on the level and the processor you're designing. It depends on your, essentially the access pattern. For example, you might have an application that you don't update much. So you write to a cache block, and then you don't have many writes after that. So if that's the case, maybe write through is a better case. But if the application and basically access pattern, you have many writes, frequent writes to the same block, then you might prefer write back. So the reason we have trade-off here, that shows to you that there is no basically a definitive answer to this question. So it really depends on your design decisions in the end, and also your access patterns. Okay, another important question in handling writes is that, do we allocate a cache block on a write miss? So you access, for example, L1 for a write, and then you couldn't find your block in your L1, and you have write miss. So do you allocate on write miss? If we do it, we basically call it allocate on write miss policy, or we can have no allocate on write miss, which the answer is no to this question. Meaning that you have a write miss, you basically go to the next level, to the level that you can find your cache block, and then just only update that block. You don't bring that block to your L1 cache or the level that you have miss. So that's a no allocate on write miss. But if your policy is allocate on write miss, essentially you go to the next level, you write it, and then you bring the updated data to your L1 cache to hopefully have future hit in it. So that also gives you the idea here. So we can combine with allocate on write miss, we can, similarly to write back, we can combine writes instead of writing each individually to next level. And this is also simpler because write misses can be treated the same way as read misses. So for read misses, we know that, okay, when we have a read miss, we go to the next level and that we find the data and we allocate to our cache. So we can handle write misses similar to also read misses. But then that requires transfer of the whole cache block. That might not be useful. Maybe you only want to update 1 byte in that cache block. So why are you loading the whole cache block to your L1 in order to update it? Especially when you don't want to use that block a lot. So again, it depends on your access pattern. So if you have a allocate on write miss, so you update a block, and then you're gonna also read from that block a lot, you know? So in that case, allocate on write miss makes sense. But sometimes you write, and then for some time in near future, you're not gonna access that block at all, you know, for reading and writing. So maybe in that case, you don't need to allocate it. So in such scenarios, no allocate is better because conserves cache space if locality of written block is low. So if the locality is not, for that specific block is not that high, so essentially you are better, you're utilizing your cache capacity better. And that can potentially provide better cache hit rate. Any question? Okay. Another important question in handling writes is what if the processor writes to an entire block over a small amount of time? Yeah. So basically, is there any need to bring the block into the cache from memory in the first place? So the processor wants to write to an entire block, but for some amount of time. Do we need to bring the whole cache block from the memory to the processor in the first place, or we can bring it partially? Basically, why do we not simply write to only a portion of the block, which we can call it sub-block? Example is that 4 bytes out of 64 bytes. Like you have a 64 bytes block, and you just want to update only 4 bytes of that block. Why not only updating that 4 bytes in your cache block? So the problem we have here is that the valid and dirty bits are associated with the entire 64 bytes. Remember that in our tag array, we add valid and dirty bits for each block. So we don't have, for example, valid and dirty bits for each individual 4 bytes, for example, here, right? And the way that we handle this issue is that we define this sub-blocked cache or sector cache. And the idea is that we divide the block into sub-blocks or sectors. And we have separate valid and dirty bits for each subblock, essentially. So we allocate only a subblock or a subset of subblocks on a request. So we only allocate some subblocks or only one subblock to your L1 cache or to the cache that you are accessing more. And basically you update that. So other subblocks, you don't allocate them in the beginning. Maybe in future, if you're accessing them and you need them, you will bring them. So of course, the upside is that no need to transfer the entire cache block into the cache, which is very good. So a write simply validates and updates the subblock, and that gives you more freedom in transferring subblocks into the cache. So a cache block does not need to be in cache fully. So how many subblocks do you transfer on a read? We can also think of implementing this idea for read also. In the past, whenever we have a read miss, we were moving the whole cache block to the cache. But here we can think of, okay, maybe I don't need to move the whole block. I can just move part of that block, some subblocks, maybe only forwards of that block to the cache. And that can save you basically energy and also performance, because you don't need to, you're utilizing bandwidth less here. So that's, of course, more complex design, more valid and dirty bits, and also may not exploit the special locality fully. So you should be careful when you are implementing this kind of idea. So when you have a block, and so you miss on a byte access or word access, and then you bring the whole block to your cache, the whole idea is to benefit a lot from special locality, right? But now that you are not loading the whole block and you are just loading some blocks, some sub-blocks of that block to the cache, you may not exploit the special locality well. So you should be careful to not basically cause a low hit rate because of this issue in your cache. Question? Okay. Another decision that we need to make is about how we handle instruction cache and data caches. Do they need to be separate or unified? So first, let's look into pros and cons of unified cache. So when they are unified, dynamic sharing of cache space. So you have a shared space that you are using that shared space for L1 data, for example, cache, as well as L1 instruction cache. So that provides better overall cache utilization. Why I'm saying that? Because when you have a separate cache spaces, meaning that you have an instruction memory, instruction cache, and you have a data cache. And for some specific program, you might not benefit from that instruction cache much, like the capacity, because your working set might not be that big. Similarly, also for data cache, there might be some application that your data footprint is not that huge. I mean, it's not that much. So you are not utilizing that data cache much, but you need a higher capacity for instruction cache. So once you are designing the whole idea, this two structure in a unified manner, so you have a unified structure and you're managing instruction and data cache together, potentially you can have better utilization. So there is no over provisioning that might happen with the static partitioning of cache spaces. But unfortunately, it also comes at some cons here, which is instruction and data can evict or trash each other. So there is no guaranteed space for either. So basically, your accessing to your data cache can cause eviction to your instruction cache, and so on, and the other way around, vice versa. I mean, with your policy, you can also try to control that with some technique. There are works about that. But more importantly, I would say that instruction cache and data, instruction and data are accessed in different places in the pipeline. And that's the main reason, actually, that people decided to have separate instruction, at least at the L1 level. They decided to have separate L1 instruction and L1 data cache. Because in your pipeline, first, in the beginning of pipeline, you want to fetch instructions. So you're accessing your instruction cache to fetch instructions. And then later on, in later steps of your pipeline, you want to access your data cache or data memory to read data or to store data. So you want to have a memory which is close to that part of the pipeline in order to have fast access. Similarly, also for instruction, if you have a unified memory access, unified memory space, then you cannot put it close to both fetch logic and also the memory access logic, essentially, data memory access logic. So that's why basically people decide for the first level caches, they decide to use almost always separate. So L1 instruction and L1 data cache are separated very usually in our systems, but mainly for the last reason I said. But other level cache are almost always unified. So L2, for example, you don't have separate. You have unified L2 for data and instruction, L3. Also in your DRAM, they are unified. So, so that's the idea about this. Question? Okay. Also, now let's look into multi-level cache design management. So we discussed about this hierarchy. We might have different L1, L2, L3. We already also discussed a bit in previous slide that, for example, about this having this unified or separate, depending on the level of the cache, we might decide differently. And that's actually the main reason you have different, essentially, constraints and optimization goals in different levels. So at the L1 level, the most important thing for you is that you want to be fast. Because in order to keep your pipeline full, you should be able to access your L1 cache very fast. And that's the most important design decision that you should consider. So that's why L1, for example, caches are not very large. I mean, they are relatively small. Also, people use fast transistors, fast SRAM, because you can use different technology for transistors. Also, you can have different way of implementing SRAM that can have different latencies. Or for L1 cache, people try to have it as fast as possible, and that's the main reason for them. So decisions very much affected by cycle time and pipeline structure. In first level cache, we are small and we use lower associativity because, again, we want to have low access latency because latency is critical for us. And tag store and data store are usually accessed in parallel. So basically, you access your tag array, tag store, and also data store at the same time. If you hit in your tag store, then perfect, it's good. The data that you also load from your data store is also good and useful. But if you miss in the tag store, the data that you fetch from your data store is not useful anymore. So that's the overhead that you're paying here. But people decided to pay that overhead because they want fast access latency to their caches. However, for second level caches, we have different trade-off here. So decisions need to balance hit rate and access latency for second level caches, for example. So they have usually large and highly associative caches because latency is not as important as L1. And tag store and data store can be accessed serially, which is important, especially here because your data store is quite big. It's a large array, several of megabytes. So if you hit, so you access your tag array. If it's a miss, basically you don't access your data array at all. And that can save you a lot of energy, which is very important for second level caches because those caches are big or much larger. But if you hit, access your tag store and you hit, then you access your data store to fetch your data essentially. So that comes at the price of some longer access latency in your hit, but maybe that's not that much important because in L2 and L3, we are much further from the L1 cache, and the pipeline design is not basically is not heavily dependent on the access latency of L2 and L3, for example. And for further levels and larger caches, essentially access energy is a larger problem due to cache sizes. So tag store and data store are usually also accessed serially. And there are a lot of design decisions that people are making in order to reduce the energy consumption of these large caches. They may actually use also different memory technologies, like some emerging memory technologies instead of SRAM, that they are basically more capacity optimized, and also they consume less energy. So there are a lot of design tricks that you can also think of when you have different trade-offs and constraints and goals, optimization goals in different cache levels. Any question? Okay. So yeah, we already talked about this serial and parallel access of cache levels. Essentially in parallel, no, sorry, this is actually different. This is about when you access your L1, do you also in parallel access other levels in your cache or not? So you access L1, do you also access L2 and L3 at the same time or not? So in parallel, next level cache access in parallel with the previous level, which is a form of a speculative access, because you say that, okay, if I miss in L1, at least I want to issue the access to the next level earlier, such that I can hide some of these latencies. And that's the parallel access. In serial, basically, next level cache access only if previous level misses. So of course, in parallel access, we have faster access to data if previous level misses, but there is unnecessary accesses to next level if previous levels hits, of course. In serial access, we have a slower access to data if previous level misses, and there is no also wasted accesses to the next level if previous level hits. So that's a good thing about serial accesses. Next level does not see the same accesses as the previous one as well. So this is also very important to think about. So in serial access, you only access the next levels when you miss, meaning that your upper level, like L1, for example, is acting as a filter to L2 and L3. And that would affect the locality that you're observing in those levels. So normally, usually people see less locality in, for example, L2 cache, in L3 cache, or let's say different locality. So you need to be careful when you are designing your cache, your replacement policy, also when you're designing your prefetching technique, because the pattern, the locality pattern are different at L2 level, at L3 level, and so on and so forth. Because those previous cache levels, they are filtering a lot of accesses, and your observation of locality is going to be different. So management policies are different across cache levels in the end. So just to give you some example, in this architecture of Apple M1, for example, we have both L1 and L2, which they are private to cores, but at the same time, we also have shared level cache, which is shared across CPU cores, GPUs, and accelerators, for example. So that's another decision that you might also need to consider. For example, when you have different processing elements, you don't have only, for example, CPU, because GPU and CPU are sometimes there are some applications that they are collaborative, and you are using GPU and CPU together in order to accelerate them. Then having a shared level cache that can serve both at the same time can be a good thing. But at the same time, managing this shared level cache across GPU cores and CPU cores is going to be also very difficult, because the way that GPU and CPU are access the memory, they are very, very different. GPU is heavily throughput oriented and send a lot of memory access to the memory. But on the other hand, CPU application are usually latency oriented. But essentially, in our modern architecture, we have deeper and larger cache hierarchies, and all of it because people make caches larger and hierarchy deeper in order to tolerate essentially the data movement problem. The bottleneck of bringing data from slow memory to the system to improve the performance and also energy consumption of the system. Here is also another design for AMD, which you can see the size of L1, L2, and L3 caches. This is another architecture for AMD that they use a 3D structure for L3 in order to make it even larger. So they have additional 64 megabyte L3 cache die stack on top of the processor die. This is also architecture from IBM Power 10 in 2020, which essentially also have different levels of caches. In GPU also, as we discussed, we have L1 cache, L2 cache, but also in GPU we have a scratchpad memory, which in NVIDIA terminology they call it shared memory. And that L1 cache is actually hardware managed, but the scratchpad memory, as I said, is software managed. So the programmer can decide what to do with the scratchpad memory. So in that, the structure is actually unified. For example, 192 kilobytes of data per SM. And this capacity can be used as L1 cache and or a scratchpad. So basically, the programmer can decide how much the program wants to allocate to L1 cache and how much the program wants to allocate to scratchpad memory, for example. using that 192 kilobyte of data. This is also for NVIDIA Hooper, which you can see L1 cache or scratchpad is still. NVIDIA have this solution that they have this unified structure for L1 cache and scratchpad memory, and programmer can decide based on that. And the L2 cache is there. I should also say that L2 cache, I think I said, we partially said actually in our GPU lectures, but essentially L2 cache was not there in NVIDIA GPUs before 2009, I guess. So at some point, NVIDIA in Fermi architecture, I believe, they added L2 cache because they realized that they cannot tolerate memory accesses, essentially. So the memory bandwidth was heavily saturated for many of these applications. So they had to basically make cache hierarchy deeper and larger in order to reduce a bit of memory bandwidth saturation, essentially. Okay, and this is also another architecture of NVIDIA you can check. People also have looked into many different ideas. This is also, again, for NVIDIA. So in A100, which is Ampere GPU, you have this feature that you can directly copy from L2 to your scratchpad memory. So when you don't, by bypassing L1 and registerify. So you don't, when you want to copy data from L2 to your shared memory, which is scratchpad memory, you don't need to go through the L1, also register file, and then move data to your shared memory. So you can directly copy that. So that's also one of the design decisions that essentially designer and architect should make that decision, and then software should be able to support that. And that's the whole system that they provide in order to support this idea. Another basic improvement in Hooper H100 is that they provide this direct copy from the global memory, which is the GPU device memory, to the shared memory, for example. Also, they show that shared memories, they can communicate data together. That's another support that they provided. So in multi-level cache design, as I discussed, there are a lot of decisions, like which levels to place a block into from memory, which levels to evict a block to or from an inner level, or also bypassing versus non-bypassing levels that we already also seen in some of the example. Like when we wanted to bring data, for example, from L2 to the shared memory on that example, we simply bypass L1, for example, caches. So people have defined these inclusive, exclusive, and non-inclusive hierarchies. Inclusive says that a block in an inner level is always included also in an outer level, meaning that if a block exists, for example, in L1 cache, that block definitely exists in L2 cache as well. And also, if L2 cache is also inclusive, that block should be also in L3 as well. That's inclusive. Another, with inclusive cache, that simplifies your cache coherence. That we don't get to that today, but we can hopefully discuss it later. Exclusive caches, a block in an inner level does not exist in an outer level, for sure. Like if the block exists in L1 cache, that block definitely does not exist in L2. That's for sure, because that cache is exclusive. So this is good, better utilizes the space in the entire hierarchy. So in inclusive cache, you are duplicating data a lot. So you are duplicating a lot of access data that you have in L1, you need to duplicate all of them in L2. Also, everything in L2 you need to duplicate. If L2 is inclusive, you also need to duplicate in L3 and so on and so forth. But in exclusive cache, you don't duplicate, and that better utilizes space in the entire hierarchy. But then there is also another way, which is non-inclusive, which basically you don't care. So a block in an inner level may or may not be included in an outer level. That relaxes design decisions. Meaning that, for example, when you access data, access L1 and you miss, you go to L2, you may find your data from L2 and you bring your data to L1. So if you are inclusive cache, you need to make sure that this L1 and L2 both keep the data together. But when you are non-inclusive, you don't care. So L1 may keep the data, but L2 for some reason might already evict it, basically that data. So that data that block might not exist in that L2 anymore because of eviction policy that we might have. However, in inclusive cache, if you are evicting something from L2, you also need to, if that block exists in L1, you also need to evict from L1 as well. So that complicates the whole design, actually. So that's why many of the caches also, they are non-inclusive, because that relaxes a lot of design decisions for us. Okay. Any questions? Okay. I think I will stop here. I wanted to cover more, but the topic actually is not easy to convey. So I think I went a bit slow, but that's perfectly fine. Next week on Thursday, we will pick up from this part. And then we will hopefully get to more advanced topic like prefetching, caches, and so on and so forth. So wish you a nice weekend and see you all next week.